Hello everyone, welcome to another physical science lesson. We're getting into relationships and we're going to be talking today about how to represent relationships. Now I'm not talking about drawing hearts and carvings on trees or anything like that, or writing little notes or sending messages. No, we're talking about real relationships, the relationships that you'll find in physics. So let's go and have a look at them. So if you remember, we're talking about relationships. There are different types of relationships in physics and in chemistry, and we can classify these in terms of the most important one, the most useful one, is a directly proportional relationship. We've also spoken about something that is inversely proportional. We haven't really mentioned the squared relationship. We're going to talk about that today, but the critical focus is how we represent these. Now, relationships can be represented in words, tables, and graphs. Today, we're going to focus on this relationship, the relationship between graphs and equations. And so you might have wondered, where do things come from when we're dealing with our physical science textbooks? We'll see suddenly an equation pops up or a graph is drawn. What's the link between the things that we observe, the data that we look at in an experiment, the graph that we draw, and the equation that we use to solve problems? Well, that's exactly the question we're wanting to ask. How do scientists link graphs of data to an equation? Well, hopefully by the end of this lesson, you'll be able to answer that you know exactly how we're going to do it. So let's focus and let's get together our initial terminology, things that we've learned of before, and things that you're going to need to remember as we go through this section. And in fact, all sections of physics and chemistry. So the first thing that I want to talk about is just quickly recap this word directly proportional. I said earlier it's the most important relationship, and you would remember that when something is directly proportional, we have two variables. Let's just take, for example, A. We say it's directly proportional to F. Then that's the way, the notation that we're going to write it. We also remember that if you were to draw a graph of A against F, then what you're going to do is you're going to see that this graph is a straight line graph that passes through the origin. The independent variable is the one that you choose to control. It's this force that we're going to be controlling here, and the acceleration for A is the dependent variable. It's the outcome, the result of you applying a force to an object. So please bear in mind these factors as we're looking at graphs and we're thinking about relationships. Which one are we controlling? Which one is a result of the experiment that we've set up? Now, what's so nice about the directly proportional relationship is it's very easy to go from the graph to an equation. And we're going to show you exactly how that works. So let's take a very simple example that everyone is familiar with, an object moving at constant speed. Now, when an object moves at constant speed, I'm going to just illustrate what that looks like. If that's the starting point, so that's the initial point where we're going to start the clock and we're going to say time equals 1, then after a certain amount of time, what we're going to find is the object has moved. That's time equals 2. In the same time interval, we'd find that there's moved an equal distance. So if we were to compare these distances that have been moved, you'll see they're roughly equal. In each of the time intervals, we'll find we have equal distance in equal time. And so what does that mean for the graph? Have a look carefully at what it means for the graph. And I want you to watch this very carefully because it's very important. In each time interval, time intervals, remember, are the same. You're going to see that the distance that is increasing is the same. So if I were to say that was T1, let's call that T2. And I'm doing this quite roughly. But you'll see that the object has moved a certain distance. The distance that it moves, I'm indicating with the blue arrow there. Now, if I went a further distance, I went from T2 on the graph to T3. There's my T3. I'm going to do the dots up like that. And you will be able to compare, even though I've done it very roughly, that distance is about the same. So in equal time, it's gone the same distance. And so we could carry this process on. What that is meaning is that we're going at a constant speed. We're not speeding up. We're not slowing down. We're going at the same speed throughout the measured time. Okay, now, having got that idea, let's have a look at the graph from a mathematical point of view. What are the features of this graph mathematically? Well, the first thing that you'll notice is it's a straight line. It has a certain steepness. We call that steepness the gradient. And the gradient at this position, and the gradient at that position, and the gradient at that position is all the same. It's a constant. Now, remember how we work out gradient as well. We can take gradient and we can say it's the change in distance over the change in time. In effect, it was what we've just done previously by seeing it was the same. We can say, what was the change in time over the change in distance? Change in distance over here, and the change in time over there. And for whatever number of triangles we want to draw, these will come up to be exactly the same because it has a constant gradient. Now, the second feature of this graph is that it intercepts at the point 0, 0. In this case, it cuts the y-axis and the x-axis at 0, 0. So this is a special line function or a line graph, and we need to take a note of the form that it forms. All line graphs have this generic form, y equals mx plus c, where the y stands for the dependent variable, where the x stands for the independent, the c stands for the intercept, and the m stands for the gradient. Now we can see here the gradient is constant. We recognize this c is going to be 0. So when we put this all together to try and make an equation that relates distance and time, it shouldn't be too difficult to see how we're going to do that. To make it look like this sort of an equation, the first thing we recognize is we've got the gradient. The gradient, the m bit, is actually just the ratio between distance and time. Because this is a constant, we can say the distance is directly proportional to time. If we go to the equation now, we can see that there we've got distance divided by time is a constant. If we double the distance, we have to double the time. If we multiply the distance by a half, we have to multiply the time by a half. This isn't in the form of yx plus c. It's just in the form of a constant gradient. It's in the form where we're showing the gradient is the change in y over the change in x. But we can unwrap that. We can multiply through some things, and we can get distance on its own. So we're going to say, let's make distance, which was the dependent variable, is equal to the speed, which is the constant. This is the constant. And there's your time. And so if you compare these, you'll see that relates to the y, that relates to the x, the c is 0, and this is your gradient. How cool is that? Just by looking at a graph, we can establish an equation. Now, I want you to think about it very carefully while you take a short break. We'll be back straight after that. Welcome back. I hope you had a good break. Now, we've been talking about the directly proportional relationship. I want us to look at this in a little bit more detail and look at another example, one that we've seen before. In fact, it's a very famous experiment that was done by a man called James Hook. Let's go and have a look at it. So, James Hook developed this idea of looking at a spring and putting a force onto a spring, which he measured in newtons, and he developed a relationship called Hooke's law, where he related the force that he was applying to the stretch of the spring, the increase of the stretch, in effect, or the extension. We refer to that as delta x, the extension of the spring. Now, which one do you think James Hook was controlling? Which one did he have the influence over? Was it the force or was it the extension? Because you see, we need to decide which is the independent variable and which is the dependent variable. Can you make a decision? Have a look at it carefully. The force was applied and it caused the spring to stretch. So that tells me that the force is actually the independent variable. And the stretch is going to be the dependent variable. Now, if we've got an independent and a dependent variable, and we're going to draw a graph of that, where do they go? Well, you need to remember this. The independent variable always goes onto the horizontal axis. The dependent variable always goes onto the vertical axis. So when we draw the graph, we're going to draw it like this, where we say the force, that's the independent, and this one is the dependent. And we're going to construct the graph. And what you notice in this situation is that we've got the words written as the title of the graph, where we take the first thing is the dependent variable, and we say that that's the relationship we're looking at, the dependent versus the independent. And it kind of goes in that order, which sometimes confuses people. So it's very important that we see this relationship from the graph of what's dependent, what's independent. And the next thing is to look and see the characteristics of this graph. Notice that the graph goes through the origin. So it is halfway there to being a directly proportional relationship. It covers that one condition. It goes through the zero. The next thing we notice, it forms a straight line. That tells us the gradient is constant. So it is in the same format as a straight line graph. And so it has a constant gradient. We can work out the gradient by looking and seeing the change in the force. So the change in the force would be written over there, and the change in the extension would be written over there. And we can measure that by looking at the different coordinates on a piece of graph paper and working at that. In the end, we're going to take the value for the dependent variable and divide it by the value for the independent variable. And in the end, we're going to say that because of the graph structure, we've got the change in x is directly proportional to the change in f, or simply x is directly proportional to f. This little alpha sign says in shorthand directly proportional. But now I want us to try and go from this graph to what the equation would look like. Yes, we've got an equation for the constant, for the gradient, and in Hooke's law, this gradient is called the spring constant. It's just a value for every spring, how stretchy a spring is. If it's a very hard spring to stretch, the spring constant will be a high value. If it's easy to stretch, then it will be a low value. We give the spring constant a letter K. So if we're going to put dependent, independent, and the constant together to make an equation, well, that shouldn't be too difficult. Let's see how we can do it. We're going to take it one step at a time. We're going to say, there we go. We know that the delta x, the extension, divided by the force is going to be the constant. That's going to be the spring constant. Now, I'm going to multiply both sides of the equation by that factor, the independent variable, the force. And I'm going to get delta x is equal to k times delta f. Now, that might not be very convenient for me to work with. So I'm going to switch them around. I'm just going to rewrite what is on the right-hand side here. I'm going to write exactly that on the left-hand side. And what was on the left-hand side, I'm going to write on the right-hand side. And now you can see that I've got the value k times f is equal to delta x. But guys, I really want to be able to solve for what force is going to cause a certain extension. So if I want to know force on its own, I'm going to have to take this value here, the k that I originally had, and divide it by both sides, and I'll get a 1 over k there. Now, if the equation is written like this, f is equal to 1 over k times delta x, then what I need you to understand, it's not the gradient. The 1 over k, if we go back to the graph of the gradient here, this was k. If I'm working with f is equal to 1 over k delta x, then I've got to recognize I've changed something. And I hope you can see what I've changed. I've switched over and I've made this now the dependent variable. And this is now the independent variable in the equation because I switched sides. So you've got to be very careful when you look at a graph and they say, what does the gradient represent? Be careful that you look at what the labels on the graph are and make sure that you don't mix up the k value. This is not, the k here is not actually the spring constant. 1 over k would be the spring constant if we're wanting to be totally strict about it. Okay, so please be very careful. Whenever you're looking at gradient, try and interpret what it is, but make sure it fits into the form of y equals mx, where this is the dependent and this is the independent. Right, here's another situation, a graph that we've seen before. In this case, the volume is the dependent variable. I'm just going to write DEP there. And on the horizontal axis, we've got the independent variable. And in this case, it's 1 over pressure, or the reciprocal of pressure. Now notice this graph line cuts through the 0, 0 point. We also recognize it's a straight line. And so the gradient is constant. And so we've got a recognition here that the change in volume and the change in 1 over pressure, if we took those two and we put them over each other into an equation like this, that this will form a constant. So what can we say based on the graph? Well, I think we can say, based on this graph, that volume is directly proportional to 1 over pressure. And that's a very interesting conclusion that we've come to, because it's telling us about a proportional relationship, but it includes a 1 over, a reciprocal. That's quite a word that we don't hear very often, but it's an important word to remember. Now, let's see the implication of what this gradient is actually representing and how we can use it to find further relationships. So as I've written it in words here, we've written it in symbols previously to say the volume is equal to 1 over pressure. We've written it in that form. We're saying this is a constant. What I want us to do is just to look at this very carefully and say if we have delta V over delta 1 over P. Now, what's the rule when you divide by a fraction? That's right. If you divide by a fraction, we say we tip it and we times it. So we know that's equal to a constant. So delta V times 1 over P, or delta 1 over P, is equal to a constant. So in effect, what we can say is that V times P is equal to a constant. Guys, that's quite a discovery for us, because now we can say that when we've got two variables that are multiplied together, they are not forming a directly proportional relationship, but we recognize that it's the reciprocal that is directly proportional. It's 1 over the pressure that's directly proportional to volume. What we can say when we see this sort of relationship coming out is that those two things, when they're multiplied together, they're called inversely proportional. Now, in the likes of the pressure-volume graph, what they sometimes represent this is say, let's just take some readings and let's say they're equal to each other. And if you look very carefully at that sort of relationship where you take points and you multiply them together and they give you a constant, well, that's going to not give you a straight line if you plot it, but it's going to give you a hyperbola. So we're going to say if we have pressure and volume, we're not going to get a straight line in this case, but we're going to get a hyperbola that looks something like that. But remember, a curve, we can't really tell. Is it a hyperbola or is it a parabola? Is it another function? Well, it's much easier to recognize whenever you have an inversely proportional relationship. If you plot 1 over the independent variable against the dependent variable, you'll be able to get a straight line. Okay, so let's make sure that we've got this very clear. When we represent graphs, we must make sure that we try and show a directly proportional relationship. Directly proportional relationship will always have a straight line that passes through the origin, where an inversely proportional relationship, it might come up that we've got a curved line. To try and satisfy that, what we're going to do is we're going to say the following. We're going to say, instead of choosing the dependent variable and the independent variable, we're going to change that around and we're going to say, let's take the y, 1 over x, and then it will be a straight line. It will pass through the origin, and we can say that y is directly proportional to 1 over x. So please make sure whenever you're trying to look at relationships and you're trying to look at graphs, relating them to an equation, that you must make sure that you've got them very clearly sorted out, that you understand what is the independent variable, what's the dependent variable. If those two things form together in an equation like a directly proportional relationship where you've got y is equal to the gradient m times x, then you know it's directly proportional. When you get an equation that is going to be, and that was the dependent variable, that's the independent variable, when you've got the equations that are y is equal to x is equal to a constant, then that's inversely proportional. Guys, this is so important, and it's so important that you get this right. So please pay attention, practice lots, and make sure that you've got this very well clearly sorted out. In that way, we can relate the graphs of different relationships to their equations. Right, now let's take a few moments, take a deep breath, have a break, and we'll see you straight after that. Welcome back. Nice to have you with us. We're looking at relationships. Relationships in physics and in chemistry. We've been looking at what happens when we look at a graph to develop an equation. Now, let's see if we can do the reverse of that process. Let's start with an equation and see what the equation tells us and predict what sort of graph we can get from that. So the important part that we're going to be looking at is a focus on graphs and equations, but we're going to start with equations and try and work out what the graph would look at and say what sort of relationship that would be. Is it a directly proportional, is it a squared, or is it an inversely proportional relationship? So if we have this equation, an equation that is R is equal to V divided by I, it is the equation from Ohm's law, dealing with electricity, where V is known as voltage or potential difference, measured in volts, and I is the current that's measured in ampere. Now, if we look at that equation, we recognize that R is a constant. So is there some clue that we can have as we look at this equation? What do you think it means when we've got two variables, one divided by the other, and gives you a constant? Now, I'm sure that you'll see that that's very similar to the ideas that we were having previously when we said delta y divided by delta x is equal to a constant, where this is the gradient of a line graph. And so we put those two things together and we begin to understand that this sort of equation is telling us that there's a relationship between V and I. And in fact, what we can say is that V is directly proportional to I. Or we could say that I is directly proportional to V. In this case, we're going to say V is directly proportional to I. The constant in this case is R, the resistance of the conductor that we're looking at. And so bear that in mind and now try and think in terms of what we've said earlier. What sort of graph do you think we're going to be looking at? Well, it would be one where the gradient is constant. So it's not going to be a hyperbola or a parabola, but it's going to be one that has a straight line. So here we go. If we have the V measured in volts, that is the dependent variable, and we have I, which is the independent variable, we're going to get a straight line that passes through the origin, and the gradient here is going to be R. It's the change in V divided by the change in I. And so we can clearly say that V is directly proportional to I, and we've got a particular relationship, a relationship where we can say V and I are directly proportional. But notice something. In the equation that we started with, R is equal to V over I, this isn't in the form of y equals mx plus c. It's not in the form of y equals mx plus c. Even though the graph indicates it as y equals mx plus c, it's showing you it's in that general form. And so there are two things, two ways, two equations, if you like, that can indicate for us that we have a directly proportional relationship. And the first one is when we say we've got a constant and we've got a fraction. And the second one is if we rearrange this in the form where we have the dependent variable, V, is equal to R times I. Now that one is the dependent variable, this is the independent variable, and that's the constant. And there you've got it. That looks just like the equation y equals m times x. So it's not too difficult to really see how we can switch from an equation to a graph to a relationship and backwards and forwards, and recognizing the different forms that they take. The equation either being in this form where it's a fraction, or where it's an expanded form, where it's an equation where the two variables are not multiplied together, but they're multiplied, the independent variable is multiplied by a constant that gives you your dependent variable. Okay, let's have a look at another equation. So in this equation, it kind of looks a little different. We don't see a division sign. We see a constant. Yeah, we've got a constant again, and that constant is c, and we've got two variables multiplied by each other. Now, let's take this one as the independent variable, and this one as the dependent variable. And what do we know about them? We've got two variables multiplied together to give you a constant. Well, if you remember clearly when we spoke about graphs earlier, we said if we had y and x, and we multiply them together to give us a constant, we get a hyperbola, a curve that we can't do much about. But if we took the same variables and we said y against 1 over x, now we've got a solution where we can draw that and draw a straight line. And we can say y is directly proportional to 1 over x. Its y is directly proportional to the reciprocal of x, which is the same as saying y is inversely proportional. So what you put on the bottom on the independent variable graph helps a lot to be able to describe the relationship. So if we go to our relationship in terms of f times y, we're recognizing that f is directly proportional to 1 over y. They are, in fact, f is inversely proportional to lambda. I said y earlier, that's lambda, it's the wavelength. Okay, so please bear that in mind. If we want to show that on the graph though, please make sure that you've got your graph sorted out. We're wanting a graph that looks like this one. We're wanting a straight line graph to confirm our relationship. And so look what I've got here. I've got the dependent variable, the f, and I've got 1 over lambda over there. And as a result of that, I can say that f is directly proportional to 1 over lambda. The c is a constant. When two things are multiplied by each other together, we recognize that is going to be an inverse proportion relationship. We can represent it and confirm it by doing the straight line bit as well. Okay, let's have a look at things to check for. When you're doing these relationships, please check that you want to make sure that they look like a linear equation. You want to get them into the form of y equals mx plus c. And if possible, that c should equal 0. That c mustn't be confused with a constant. The constant is this bit. This is the gradient. And these are your two variables. Check what does the gradient represent. It's very important that you understand that. The gradient represents a physical quantity. And so be aware of what that gradient represents. And decide if the variables are then directly or inversely proportional. If it's one dependent variable against another, then it's going to be a straight line. If it's a 1 over, then they're inversely. So that's the way to be able to check it. I think it's time for a quick little break, and then we'll come back and look at some more interesting equations. We'll see you then. Welcome to our lesson on relationships. We're into our last little section, and we're going to look at some interesting relationships now. And so ones that we haven't looked at before. We've been focusing on directly proportional relationships, the directly proportional relationship and the inversely proportional relationship and see how the graphs and the equations work together. Now we're going to look at the squared relationship and also look at how the equations and graphs link together. And you know what? There's no new tricks here. It's just the same sort of thing as we've done before. But let's have a look. And so here we go. Here is an equation of power, the relationship of power related to current, I, the current in a circuit, and R, the resistance. And as you can see, R is constant. So in effect, what we've got P as the dependent variable. So that's the dependent variable, and the current is the independent variable. Now, if we just look at that, it's in the form of y equals mx plus c, and c is 0. There's no constant there. There's a 0 added. So we can say that P is equal to R times I squared. And as a result of that, we can say P is directly proportional to I squared. The R being the constant would represent the gradient. Okay. Now, if we were to look at the graph from the data, we might be tempted to say, so what's the relationship between P and I? And if we did that, we'd get this sort of graph. P against I, where I is the independent, because it's on the horizontal, and P is the dependent, it's on the vertical. Even though R, it looks a bit like a parabola, but we can never really tell. It's in the form of y equals ax squared. So it looks a bit like a parabola, but we can't be sure because curves are funny. Never worry too much about curves. What you want to look for is a straight line. So how are we going to change it to confirm our prediction? Well, we're going to plot the graph not of P against I, but notice we're plotting against I squared. So because we've got P as the dependent variable, we're making I squared the independent variable, and now the line will be a straight line. And the gradient here will be the change in power over the change in current squared. That's going to be your constant, and that constant is going to be equal to R. And so it's a really nice thing to see that similarly to the way we dealt with the inversely proportional relationship, where we looked at a 1 over the variable, we're looking at a squared relationship here. And if we take the variable and square it and compare it to the dependent variable, we'll get a straight line. And that's how we can show that they're related in the equation like we've seen over there. So the equation predicts for us what is the independent, the dependent, and what's the constant. I hope you've got that. But let's just have a look at a little bit more interesting one that's a little bit more involved. Now, this is known as Coulomb's law. And it's something to deal with electrostatics. It tells us about the force between charges and the relationship between the force and the distance between the charges. So we need to make very clear that this equation is quite complex and it can tell us more than one sort of relationship. But from what we've seen previously, I think we can break them down and try to see what the equation is telling us. And so the first thing that I'm going to do is I'm going to split out those two and say, let's make them a variable. Let's make those, in fact, the independent variable. So it's the product of the charges. And we're going to say force here is the dependent variable. Then notice this would be representing the gradient. K divided by R squared, if K and R are the constants. So what do you predict? Well, if we draw a graph of Q1 times Q2 and put the values of that on the horizontal axis and put the vertical axis as the force, then what are we going to get? Well, you've got it. It's a straight line. The force in newtons, Q1 times Q2, coulombs squared, straight line that passes through the origin, we can say that force is directly proportional to Q1, Q2. And what does this gradient represent? Yes, it's the change in force divided by the change in the product of charge, but it's actually equal to K over R squared. So it's the universal field constant, or the electric field constant, divided by R squared. Okay, so very important for us to see that particular relationship there. Now, let's have a look and let's separate out. And if we were doing a relationship now and said, well, let R be the independent variable. So let R be the independent variable. This is the dependent variable. Let's make that the constant. So K, Q1, Q2 are constant. What sort of graph do you think we will look at now? What sort of relationship can we start to see? Well, you will see that when you've got the things in the form of y equals m, which is standing for the constant, x, then we can say y is directly proportional to x, which means that f is directly proportional to 1 over r squared. So I want to take a note of that. F is directly proportional to 1 over r squared. This is no longer a squared relationship. It's known as an inverse square relationship. And so by looking at the graph, we will be able to tell whether it's an inverse square relationship if we plot 1 over r squared against f. And that's exactly what I've done here. And you'll see there I've got meters to the minus 2, 1 over r squared, straight line graph that goes through the origin. We can say that f is directly proportional to 1 over r squared. These other factors, they're constant. So what's the gradient going to be? Oh, you've got it. This gradient here, m, is going to be equal to the constant, which is k, q1, q2. Okay. Excellent. I hope that you've understood that principle. So whenever you look at an equation, you can separate it out and start to define the relationships in words. And so coming back to this one, well, there are two relationships that I can see. I can say f is directly proportional to q1, q2, and I can say f is directly proportional to 1 over r squared. Remember, when we say directly proportional to 1 over r squared in words, we can say that means that f is inversely proportional to r squared. And that's a fantastic discovery. It's an important relationship. Remember what we said when we said inversely proportional. If the one increases, the other decreases by the same proportion. And that's what we're going to see here. But the square plays a little bit of an important factor there. So as the one increases, the other will decrease by 1 over r squared. It's going to change the factor a little bit. But we're not too much worried about that. I just want you to get the relationship. Now, let's have a look at our final equation that we're going to look at. Now, this equation definitely has a dependent variable. We can recognize it's even y. It's on its own. Then we've got something that is looking quite strange, that is on its own, and it's got u and t with it. Then we've got something that says half a, and we were told that a is constant, and we've got a t squared. So this really looks quite a mystery. How are we going to unpack all of this? Well, here's an idea. Can we perhaps switch things around to make them look like a straight line? Can we put them into a format that looks like the equation for a straight line? So that's exactly where I'm going to start. I'm going to say, let's call this my dependent variable. And I'm going to now say, because that's a constant, let me switch that around and say that's half a t squared plus ut. Now, I haven't told you anything about what those letters stand for, and I think that's probably an important thing that I should do at this point. But before we get there, let's just take a note of something. Let's take a note that we've got a constant here. The bit in front of the t squared is a constant. This is a bit on its own. So if we were to write y equals mx plus c, then the c corresponds to the ut, the half a corresponds to the m, and the x corresponds to the t squared. So here we've got a very interesting relationship. Even though we've got t in two parts, we need to understand that we can simplify it a little bit. And to help us, the u there stands for speed. Okay, so the u stands for speed, and the t is for time, and the y stands for distance. And like we've said right in the beginning, when we take speed times time, we get distance. So this factor here represents a distance. And so if we go to our graph, and remember this is a distance as well, then we'll see that y against t, we've got a distance, an initial distance that is put over there. That is representing distance. This represents time. And in this case, what we're saying is it's no longer a constant speed. The speed is changing. Look what's happening. The gradient of this line is changing. So over here, the gradient is not very steep, but here the gradient is steep. That's what happens with the parabola. The gradient is changing. This is an example of a graph where an object is speeding up. It is accelerating. The A stands for acceleration. So very quickly, let's go to our next graph and say, if we were to look at this and say, let that be that's still over there, let's make sure that we're going to plot against t squared now. We've got a constant over here. The gradient is constant. That's going to be our value there. And we can say that the y is directly, no, we can't say directly because it's not going through the origin. So what we've got to do is we've got to make sure that this ut part here, the u has to go to 0. And only then can we say y is directly proportional to t squared. Guys, I think we've more or less covered all the different types of relationships. Let's just do a quick recap. Remember, when you have a directly proportional relationship, it's represented by a straight line that passes through the origin, and we must try and represent it in the equation form of y equals mx. That is the most important thing that you've got. So look at equations and see if you can represent them in this type of form. Thank you so much. I hope you've enjoyed that lesson and you've learned more about relationships that we find in both physics and chemistry. From me, so long, goodbye.